Okay, so the next property we're going to take a look at is the melting point, and this is going to be the properties of solids now. Melting point, we'll abbreviate as MP, and the melting point is of a substance, of a solid specifically, is defined as the temperature at which the energy of the individual particles enable them to break free of their fixed positions, and then that actually allows them to now turn into the liquid phase. Right, remember, in the solid phase, the particles are locked in place, and in the liquid phase, they can just move past each other. So the temperature at which that transition happens is known as the melting point of a solid. Just like with the boiling point, you're going to see some trends here as well. So the melting point is depends on the intermolecular forces of attraction as well, and there's a direct relationship. Okay, stronger intermolecular forces, right? That means that they're glued very closely together. It's going to require a lot more energy to force them to break free from each other. So that means that the melting point is going to be higher. So stronger intermolecular force would mean higher the melting point. And you can actually see if you would a chart, for example, all of the hydrides of the group 6 elements. So we have the hydride of oxygen, hydride of sulfur, hydride of selenium, hydride of tellurium. We see there's a general trend going up. However, water is anomalously high. Okay, so it's unusually high melting point for this. And then you'll actually also see for the hydrides of the group 5 elements, so things like ammonia, um, the hydride of, I'm sorry, so that's a hydride of nitrogen, hydride of phosphorus, hydride of arsenic, hydride of antimony. Again, you see a general trend upwards. However, ammonia is also unusually high. And if you look at the hydrides of the group 7 elements, so the hydride of fluorine, the hydride of chlorine, the hydride of bromine, hydride of iodine, again, there's a general trend up, but the hydrogen fluoride is unusually high. So what's the reason for these unusually high melting points for the hydrides of those 3 elements? And that's due to hydrogen bonding that is not present, and it's strong, remember, that's one of the strongest intermolecular forces of attraction. It's not present in all the other ones that we see here. Right? So the fact that you have the hydrogen bonding present between water molecules, between ammonia molecules, between hydrogen fluoride molecules, make them stick together a lot stronger. And as a result, to separate them, you need a lot more energy. And as a result, the melting point is going to increase. And we see a general trend here as well. If you look at the substances and their melting points in this table, what you generally see is that substances that have really weak intermolecular forces, so if they only have dispersion forces, so just the ones with dispersion forces, their melting points are super low. Remember, dispersion forces are the weakest, and everything has dispersion forces. So the substances that only have dispersion forces means it's very easy to separate them from each other. You don't need to provide a lot of energy. As a result, the melting points are going to be low. If you compare that to other substances that have some of the stronger intermolecular forces of attraction, so let's make a fair comparison here. Let's compare 2 substances that have fairly similar molar masses. So if we were to compare something like, let's compare the lithium fluoride, this one, with a 25.9 molar mass to something like fairly close to it, let's say fluorine, 38, right? Even though the lithium fluoride has a lower molar mass, it has a much higher melting point because in addition to the dispersion forces you have between the lithium fluoride, you also have ion-ion, which is the ionic bonding forces which are very strong, first of all, which make the melting point very high. Right, so again, a direct relationship between the strength of the intermolecular force and the melting point. Stronger intermolecular force, higher the melting point is going to be. Now, the last thing we'll take a look at here before we go on to the next section is the fact that we normally associate liquids as having vapor pressures, but in some cases, solids also are going to have vapor pressure associated with them, and that this is just due to the nature of the solid itself. Okay, typically the vapor pressure of solids are usually very, very, very low at room temperature, but there are a couple exceptions to this. All right, and in the case here, we have three examples. You have something like these mothballs. If you've ever used mothballs, you know they have a very distinctive scent or odor or aroma associated with them, and they're actually solids. And they used to be naphthalene, or sometimes they use camphor now. And these have high vapor pressures. They're actually able to go from the solid into the gas phase directly. Another example is iodine. I2 is a solid. It also goes from solid to the gas phase under normal conditions. And if it goes into the gas phase, it will will have vapor pressure. And iodine has a very characteristic purple color associated with it. And then the last one that's shown here, it's not readily apparent, but this is CO2. It's carbon dioxide. This is solid CO2. And this is going directly into the gas phase. All right, solid CO2 is commonly known as dry ice. You probably have used this before, and it's super cold. Under normal conditions, it goes directly into the gas phase. And depending if it's in a sealed container like this one, the vapor pressure can become so high that it'll actually cause the container to explode. That's something you want to be aware of. If you use dry ice, it does vaporize, has a very, very high vapor pressure under normal conditions. So yes, some solids can have appreciable vapor pressures, even though we think of them as having really low ones. There are some instances where they can have, in some cases, very high vapor pressures.